Hello everybody, welcome to my man cave and to my video where I hope to explain a few questions. Now, I am a retired mathematician with a great interest in astronomy over the last few decades, and as far as I am concerned, at the moment there are too many unanswered questions in astronomy, such as, is space expanding? Hubble thought so 100 years ago when he was observing. Is space finite or is it infinite? Are there hidden dimensions? What existed before the Big Bang? How did the infinitely heavy point mass causing the Big Bang arise? That's called the primordial atom. Nobody knows where it came from. Hubble's law allows speeds greater than the speed of light, and this isn't allowable. Why? And how do we fix it? Hubble's constant looks complicated. It says that for every megaparsec, which is 3.3 million light years, you'll increase your speed by 70 kilometers per second. Now that's okay, but the speed of light is reached after 14 billion light years at that basis, and that's not allowable. So there will be so many objects in space at a greater distance than this. Are they all moving faster than light? Some TV programs seem to suggest so. Right, number 6. What's the cause of Hubble tension? And Hubble tension is the fact that you've got more accurate instruments giving inconsistent results with the earlier values. Nobody knows why. Why is the expansion of our galaxy accelerating? Sorry, of our universe accelerating? Again, nobody can say. How can there be black holes with masses in the region of 1 trillion suns? Different class of black hole to when a star dies. These are called stupendously large black holes, and we'll deal with them shortly. There is a vacuum energy catastrophe, and this is theoretical value of energy density exceeding the observed value by over 10 to the power 124. Unbelievable! So what's wrong with the theory? Do we live in a single universe or a multiverse? Astronomers seem to be adopting the multiverse, but they don't know how it arises. No mechanics for it are known. And rather facetiously, why can't astronomers answer any of these? And so I got frustrated, and I think that this is not acceptable with all the results that we have these days. And so here is my solution, and everything is verifiable, either using existing or new data. So here we go. I'm starting off with a model of the universe. This represents the typical galaxy. It has mass m, speed v, is spinning and is just moving through space. What is its energy? And there are lots of factors in this. There's kinetic energy, potential, rotational or inertial, forward and reverse attraction by those galaxies in front or behind. There's heat. There might even be some other considerations. All but the first will change the kinetic energy. Every one of these will either add to or detract from the speed that the galaxy is moving. So each can be modelled as a multiple of the kinetic energy. And in fact, there's a theorem called the virial theorem, which relates PE to KE, and so that is a multiple. So everything becomes a multiple of KE, tidy it all up, and out comes this beautifully simple equation. And this is absolutely pivotal in understanding what's going on. This says two numbers are multiplied together and give you constant value. That means if one goes up, the other must go down. And this one very important. The mass of the galaxy is going down, so the speed of the galaxy must go up. Our Sun is an average star, but it loses about 6 million tonnes per second of matter in the fusion process converting hydrogen into helium. That matter is converted into energy and is a phenomenal amount. The Milky Way loses in total about 1.8 billion tonnes per second. Incredible amount of energy related. Where does that energy go? What happens to it? And the answer is to increasing the speed of the galaxy. An increase in speed is called acceleration. And that's what the universe is demonstrating. So, let's carry on. So we find that for the last 13 billion years since forming, all galaxies have been accelerating away in every possible direction under their own steam, just burning mass, giving the impression that space is expanding. And this will be under the action of a mysterious repulsive force of some sort. Hubble interpreted this as space growing and deduced his law from simple observations. Staggering speeds have been attained, typically as demonstrated on TV by Dr. Jim Kaluli whilst demonstrating redshift calculations, 10% of the speed of light. So a typical galaxy could be moving at over 18,000 miles per second. So how do we explain that? If we look at another particular galaxy called GN211, the number 11 relates to the redshift, and a redshift of 11 is extreme and corresponds to a speed of about 98% of the speed of light. At 98% of the speed of light, the dilation factor from Einstein and Lorentz is 0.2. That means all original lengths have shrunk to 20% of the original size. Time included, and as far as mass is concerned, instead of multiplying, we divide. Mass has gone up by 5 times. Over in America, Saul Perlmutter and his colleagues showed the acceleration of the universe, but they couldn't explain it. And later on, dark energy was accepted as the driving force, even though, as any astronomer will tell you, nobody knows what it is. Right, we've got this equation. From V, if we differentiate, we can get acceleration. So let's do so. This is a product, so we use the product rule, and we get, leave the first one alone, differentiate, 2v dv by dt. That's the acceleration. You can write down as v dot or a. Leave the second alone, differentiate the first. dm by dt is the rate of change of mass of the galaxy, and that's equal to constant, 0. From which out comes this formula. It indicates negative sign. However, m dot, the rate of change of mass, is negative because they're all losing mass. And so that gives us the acceleration, the absolute value of v over 2 times the fractional rate of loss of mass. If we graph this, we get a straight line. That's the theoretical. Observationally, we'll get speckle points, a scatter diagram. And this is basically Hubble's law. If you have twice the acceleration, you get twice the velocity. And twice the velocity will give you twice the distance. And so on for any other multiple. Now, the problem with this is going to go on forever. It's unbounded. It takes no account of the cosmic speed limit, which is speed of light. Now then, The relativistic effects of moving at speed v are well known and used. So for example, we wouldn't have sat-nav without the time dilation factor introduced by Einstein and Lorentz. So if I replace m by original mass divided by the dilation factor and go through the routine again. Before we do that, what are we trying to get? We'd like to see acceleration become zero at speed of light. Because if you can't go faster than the speed of light, you can't accelerate past the speed of light. So we should get, hopefully, zero acceleration. So we'll repeat the process. Missing out lots of calculus. The new formula is this. And it looks a bit messy. So we graph it. And you can see for this face region, it looks like a straight line. Now let's see. We've got the V over C term. If V is small, V over C is very small. V over C is very small. V squared over C squared is negligible. So if we cover up the V squared over C squared, you can see we're back to the original equation. And so what we've got from that is that Hubble's law is an approximation up to about the third of the speed of light. Thereafter, observed values detract from this straight line. The further along this curve we go, the more inexplicable Hubble tension is. This is the reason for Hubble tension. The straight line does not apply after a third of the speed of light. Now, this curve reaches a maximum. There's a critical speed, capital V, and that's at roughly 2/3 of the speed of light. What does that mean? Critical speed? Because we notice the acceleration starts to go down. So we've got, for V is much less than C, equation 3 becomes equation number 2. This shows that the acceleration is 0 when V is C. V is C, that becomes 1. 1 take away 1 is nothing. Acceleration is nothing. We get another 0 if the rate of change of mass is 0. If the stars in the galaxy have all burnt out, they're not losing any mass. So the galaxy isn't going to accelerate any further. It will just carry on as a burnt out cinder, moving through space at whatever speed it's going at. So we've got Hubble's law is only an approximation for V is under a third of the speed of light. I'm sure he'd understand, but he didn't take that into account when he produced his law. The critical speed is V, which is roughly 2/3 of C. Lots of mathematics gives you this exact value, but I'm not interested in that. When the acceleration maximises at that value, why does it maximise? There are two things affecting the mass of the galaxy. You have the mass burn off due to fusion. You've got the relativistic mass increase due to Einstein's equation, and at this point the two are equal. So any of the 2 trillion galaxies that make it to this critical speed, they are going to continue accelerating. They'll be getting smaller and smaller, faster and faster, heavier and heavier, and will continue until a Schwarzschild radius is reached, when the universe will become a black hole. But not a black hole like we're used to, the result of a dying star. This is a completely new, different class of black hole, referred to as a stupendously large black hole, or a slab for short. Astronomers cannot say how these are produced. They are the last stage in galactic evolution. before point mass is reached, resulting in a new Big Bang and the birth of a new universe. This will happen many times. Lots of galaxies all going to do this. Picture a room with lots of soap bubbles, all different sizes, moving in different directions. And this gives an example of the multiverse. So, each will represent a new universe, too remote to be seen by us. We might see the Big Bang if we were around, but we don't know. Many repetitions of this process require space to be unbounded, and we find ourselves living in an infinite multiverse. So we see the most awesome, self-sustaining and self-replicating system ever envisaged, the steady state that Einstein was hoping that he could prove, but was unable to. No other work produces the answers that this does. All explanations are easily understood, and most importantly, they're verifiable. Even if this means new data is required in order to determine accelerations of the galaxies. So there's no big crunch or big freeze as forecast by the astronomers, just regeneration and the possibility of new life many times over. How fantastic. Now then, let's summarise all of these. First one. Space is not growing. Space is infinitely old and infinitely large. We live in a multiverse. There's no dark energy pushing everything apart. It's self-driven by burning off the mass. And importantly, no dark energy means that there's no vacuum catastrophe, because there will be no dark energy component in the equation. Galaxies exceeding the critical speed v become new universes, and here's the mechanism for the multiverse to work. No object can ever expect to exceed light speed. Not all galaxies may have life or the same physical constants as ours. Different gravity, different electronic charge, and so on. We can't rule out the possibility of an antimatter galaxy with the possibility of anti-life. And if there is, when the aliens come, don't shake hands with them, because there'll be another Big Bang. Slabs are the last stage in galactic evolution before a new Big Bang, and, more importantly, they're evidence of the process of evolution. So for number 10, all the original questions are answered. What was it before the Big Bang? A little bit of empty space that a very tiny slab entered and then exploded. So, with the exception of number 11, why can't the astronomers answer it? And perhaps the answer is because they're not mathematicians. And so now all the original posed questions have been answered, and what a fantastic scenario it presents. Thank you for your time.